Hey, welcome to Integral Calculus. This is part 1, and we've got the fundamental theorem of calculus here. I first of all think we should go back and look at what we were doing with differential calculus. And we've got some graphs up here, some speed, time graphs, and one over here. Do you remember back in differential calculus, it was the other way around. We wanted to look at the change in displacement with time, and we said the instantaneous velocity should be a tangent there. V inst was the slope of the tangent. Remember that. Well, if we now plot the speed or the velocity, how could we get the distance travelled from that, going backwards distance? If we have the rate of change of the distance against time, how do we get the distance travelled? Okay, well, if it's a constant velocity, like 6 kilometres an hour, 60 kilometres an hour, over a quarter of an hour, we know it's 60 times a quarter. It's the area under the curve, under the straight line here in actual fact. And here's one here. If the velocity is given by 60, take 600t, and we want to look at the displacement or distance travelled, again it would be this purple area. So it would be a half the base times the height, okay, to get the actual distance travelled. So here's the same problem again in this diagram. What if it's a curve? Oh, there's the distance travelled, or the displacement, and this is the rate of change of displacement at the time. It's going to be the area under the curve. So come down here, if we had a formula for the function x squared plus 1, could we calculate this area here? I wonder if we could. And I've got some hints for you over here. Here is an estimate of that area. It's too big, isn't it? It's got all these on top, and here's one that's too small. Well, what we're going to do in this presentation now is to look at seeing if we can exactly mathematically calculate the area under a curve for a velocity time graph now that is itself a curve. Not ones like this up here where the area is a known shape, the area is the area of a known shape, a rectangle or a triangle, but rather a curve here. Let's go down and explore this a bit more. I think you're going to find this quite intriguing. So here we are. Here's our problem. We want to find the area under a curve. And if you take it back to a Newton's approach, it's because velocity time are the variables there, and this is the distance perhaps. Okay, although we're just going to do it in y and x land now. Okay, see if we can develop an approach which we can apply in different contexts. Let's go down and see how we might do it. And I've already given you a clue, haven't I? So, if we take the function as x squared plus 1, this graph looks like this. And we're going to do two things to it. We're going to draw up rectangles between 1 and 2, 2 and 3, and 3 and 4. Those rectangles are going to be slightly taller than the curve. So we'll go to value 2, sub in 2 into the function, get a function value of 5. So the area of that is 5 by 1. Now, the area of the next rectangle, which is above the line, is 1 by, what's this? 10 is f of 3. And then 1 times, what's 17? It's f of 4. The height there is obtained by subbing 4 in the function. So what have we done? If we do all those areas and add them up, we have an area above. We call it an upper area of the upper rectangles. Let's come across here now and see if we can trap this actual area that we want between two other areas. So here, the area of the lower rectangles. How do we do those? We'll go to the first value and draw it straight across. So what's the height here? That will be f of 1. That's 1 times f of 1. Because this is a width of 1, and then this height here is f of 2, so it's 1 by f of 2, getting the areas here, and 1 by f of 3, which is 10. So we get a total of 17 square units. So what do we know? The actual area is somewhere less than the upper area and greater than the lower area. So it's somewhere between 17 and 32. And you say, well, that's interesting, but that's pretty rough. We'd want to do better maths than that. So let's come down and see if we can do better. So what happens if we keep doing it? And let's say we take smaller and smaller widths of the rectangles in here. And we'll keep the same width in the two scenarios. This is the lower sum and this is the upper sum here, upper area. So what are we going to do? We're going to say it's the width times the function value for each of these along here. Just remembering the height of the rectangle will be f of, stick the x value back in the function and work out the height. And the same thing over here. Okay, so we get a big sum. The upper ones are all these multiplied. And the IB love this sigma notation. So it's the chosen width, and then the sum from t equals 0 to n take 1. Notice here with the lower sum, we use the second to last one there for the height, and over here it's the sum to n, because the upper heights go right to the end. Okay, so that's what we're doing. And so we're saying if you did many more of them, the area would still be less than the upper sum and greater than the lower sum. Now watch this statement. This is interesting. It's sometimes referred to in rough terms as a sandwich theorem. If a value is jammed between two others in an inequality and AU approaches AL, then A must also approach those two limits. Okay, so we're saying if we made an infinite number here, the sum of an infinite number of rectangles, n is infinite, then our A, the limit of that, would be our actual area that we want, and it would be the same limit as the upper value, the upper rectangle sum. Let's see if you can understand that by looking at this picture now. Okay, so here I've taken a function. This one's f of x equals x squared. Okay. And what we want to try and do, I think it's x squared, not sure now, we'll take 10 rectangles from 0 to 1, and we'll have a upper sum, this is the upper sum, and the lower sum for 10 rectangles. That's what it would look like. Look at what happens if we do 25 rectangles between 0 and 1. Okay, lots more crowding in of rectangles here, and look at what the upper and the lower sums are doing. They're getting closer together the more rectangles we draw. And can you see it looks like just a mass of rectangles? Just a mass. Oh, it's approximately the area, isn't it? I hardly see upper or lower sum differences here. So if n tended to infinity, we're saying that A would still be less than the upper sum and greater than the lower, but these two would be approaching each other if you drew many, many rectangles. And you're just getting a mass or a whole integration, if you like, of all those rectangles. Integration of the rectangles into a whole mass, integrating them, just moving them all together. So I wonder if we could somehow find a function which would do that. So here's our problem. We want an area function, don't we? So let's define A of t as the function here which gives the area from x equals A to x equals t. Let's see if we can actually find a formula for this function using maths. That upper and lower sum business was a bit rough, only estimating there. So let's have a look at the mass of it. So this is what we're going to try and do. Let's look at the area of this strip here. and this would be a of t plus h, which the area is in our newly defined a function, area from a to t plus h, minus the area from a to t, and that would give us a strip, wouldn't it? Okay, we're still looking at trying to say, as a function, what is a of x? Can we find an actual function that will give us the area under the curve? Let's do the same thing again. The area of the smaller rectangle and the area of the larger rectangle are the limits of these things here, limiting positions of these things. So what is this? Let's have a look at the lower rectangle if we drew it under the bottom there, and the upper rectangle if we drew it on the top. What would it be? Well, we've got here the area of that strip in the middle, here it is, would be between the area of the larger rectangle drawn across the top and the area of the smaller rectangle drawn underneath. Can't see it very well there. But do you agree? That strip of area is somewhere between those two values, the same reasoning as before. Well, what can we do with that? Well, let's expand it a bit and have a look at this. And this is really interesting stuff. So the width here of our rectangle is h. So, and we've taken an increasing function. You can do it if the function is decreasing as well. The inequality just goes around the other way. So let's have a look now. What can you say the area of the smaller rectangle is? That's the one coming underneath there. So what is the height of that? That's f of t times the strip width is h, and our actual strip width, going by the difference between the function values there, is that one. And then what about the height of the upper rectangle? Our upper rectangle has a height of f of t plus h. We sub this upper value into the function. So we have that as our upper rectangle expression. So our actual area is somewhere between that. Our area function gives us our actual area. Let's divide through by h. Divide everything by h. And we have a middle term, looks like that. We're saying that that middle term is greater than f of t and it's less than or equal to f of t plus h. As h tends to naught, what does it mean? Oh, can you see it? Can you see it there? The limit, I'll write it out in full so you can recognise it. The limit as h tends to naught of the a of t plus h, take a of t on h. Hey, that's the expression for the derivative of a. So, what can we say? The derivative of a lies somewhere between f of t and f of t, because as h tends to naught, this function tends to f of t. That h is tending to naught. Hey, so that means the derivative is jammed between these two values and they are approaching each other. Therefore, a dash t will be equal to f of t. The sandwich theorem, if you like. Sandwich between the two as h tends to naught. So a dash t is going to be f of t. Wow! What's that say? Well, if we want the area under, well, the graph of f of x, then what we have to do is say that the derivative of that function equals f of x. So if we wanted to find the area function, we'd have to treat this as a derivative and go backwards from differentiation. Do the antiderivative, if you like. Let's have a look at that. That's an interesting result. And here it is. Screen clippings here from a combination of Hayes, and Harris and Pearson's. So here it is for a continuous function that's defined throughout the interval with antiderivative f of x. We're going to say the area under the curve. Now hang on, that's not area. What's this? Well, that's an integral sign. The integral, that says, the integral, making as one, if you like, in simple terms. making as one all those rectangles. And why do we use a stretched out S? Because that's reflective of the sum of an infinite number of rectangles drawn from A to B over that interval where we wanted the area. We're saying if we did that, so this is reflective of our upper and lower sum approach. It means summing an infinite number of rectangles over that. So we've got the area function being between the two upper and lower sums. And what is it? It says it's f of b, take f of a. What's f? Well, f is the function which is the reversal of this as a derivative. It's an antiderivative. So f dash of x is our function. So what we've got to do is to work this problem out. Instead of drawing an infinite number of rectangles, very rough, we can do this antiderivative, reverse this f of x as if it's a derivative, come back and get f and substitute in b minus a. Wow, that sounds complicated. Here's another way of writing it. The antiderivative of a function is a function f of x such that the derivative of this function is represented like that, which is f of x. So we want to take f of x and reproduce little f of x and reproduce f of x to give us our area function. Our area function actually is the antiderivative of the function itself. Hey, that's complicated. Let's look at it in the way in which we use it. Here we are. Screen clippings from Pearson's now. So let's take f of x equals x squared. Can we discover the antiderivative? That is, if this is the function, then this must be the derivative of the area giving function. So we've got to go back to f of x. Let's just check it. Okay, if you get the derivative of x cubed, you get 3x squared. Well, that didn't work. We want this to be the derivative. We want to go and find the function whose derivative is just x squared. So we've got to find a third of it, because it's 3 times f of x. To compensate for the extra 3, we have to multiply by a third. And so we have the antiderivative, or that function whose derivative will give us our area function, is a third x cubed. Let's check that out now with the power rule. So if we say we've got a function g of x equals x to the n, then the derivative of that is nx n minus 1. What do you do if you want to go back to the derivative to the original function? What will you do? You'll increase the power by 1, we're reversing it, and then divide by the new power. That's how you'd get back, wouldn't it? Wouldn't you? Do the reverse steps. Increase the power instead of decreasing it, increase the power by 1, and divide by the new power, going backwards for the antiderivative. Because our area giving function is the antiderivative of the function itself. You've got to treat the function itself as a derivative and reverse it. Let's have a look at some. If the function was just 1, what gives us a derivative of 1? X, antiderivative. So what we want to say is we want to go back to this function as if this is the derivative. Okay, so here, what function, when differentiated, gives this? Well, increase the power by 1. Let's do it here. X to the 1, increase the power by 1, and divide by the new power. And there we have it. Okay, what about 3x squared? Let's do it this way. If that was our function, we want the antiderivative. We increase the power by 1, divide by the new power, and we'd have that. If it was x to the 4th, and that was a derivative, what would we be doing? I should put an arrow there. Increase the power by 1, divide by the new power. And this is the function whose derivative would be that. So this antiderivative is going to produce the area under the curve in most cases. We're going to see some exceptions later on. So if we had cos x, which function differentiated gives cos? It's sine. Which function which differentiated gives cos 2x? It's a half sine 2x. Let's check that one out. Because here the derivative of cos 2x is what? Oh, sorry, doing the wrong side. Derivative of sine 2x. Derivative of sine is cos. And then we've got to multiply by derivative of that function. Function of functional chain rule. E to the x is just itself. Antiderivative. Which function which when differentiated gives sine? It's minus cos. Because do you remember, if you differentiate cos, you get minus sine. And then you've got the minus in front of it, making a plus. So it's a little bit tricky here. Okay. What function has its derivative 2x? Let's reverse it. Increase the power by 1. Divide the new by new power. It's x squared. And what about another one? 1 on x. Do you remember that? That is ln x, where x has to be greater than 0. Sorry. So, or you can say ln mod x, because ln is the function which when differentiated gives 1 on x. When you come to this though, you must specify that ln is only defined if x is greater than 0, or you could put absolute value or modulus of x. Now this is interesting. It's going to ask you to go backwards through the steps to find our area giving function. Wow, we better think about that. When you do that, you can go through these. These are not actually in the course, they are the rules now. So if you wanted to find the integral that is integrating, making an infinite number, a whole mass or a whole shaded area between A and A, integrate from A to A of the function, making an infinite sum of those rectangles, well, A to A went nowhere, did it? So it's going to be 0. We can actually do it from this way. This is how we're meant to do it, using the fundamental theorem. You say you find the antiderivative, the function whose derivative is this, evaluate it at B and take away the value at A. So if you put A and A in there, they come to 0. What about the integral from B to A? Well, the integral from B to A would be the reverse of this. So it would be minus integral from A to B. Just remember, this integral here means making up an infinite number of rectangles and summing them. Think of this in simple terms as a stretched out S. That's where that symbol comes from. If you stretch out and sum an infinite number of rectangles, you get an integrated mass of rectangles, if you like. That's where those words are from. Basically, it's a simplistic approach, but it's very, very important to understand that. And we found that to actually do that infinite sum, we find the antiderivative and evaluate it across the interval. Okay, so here, if we integrate from A to B and then from B to C, right, so we're going to do it from A to B and then to C. So we could have just gone across the whole interval. That's what that's saying. Just go across, not in 2 stages, A to B and B to C, but straight across the interval. So you can see, this is designed to make you think about what this symbol means. And what if you're adding or subtracting 2 functions? Well, we're saying if you're going from A to B of f of x, you're adding A to B of g of x, you can do the 2 separately. You could actually try to prove this by writing the fundamental theorem out for each one and simplifying. I think Hayes and Harris down below here have got a couple where you're asked to do that. And the integral of a constant. Well, what's the integral? Well, infinite number of rectangles across there, but to do that we find the antiderivative. And what will the antiderivative be? Cx. That's the function which when differentiated gives that. Just remember, c is cx to the naught. If we reverse it, increase the power by 1 and divide by the new power, which means the antiderivative is cx. And similarly here, we can put the c out front. Now these are not that important in this course. Let's have a look now at applying it. What are we going to do? Use the fundamental theorem of calculus to find the area between the x-axis and y equals x squared from x is 0 to x is 1. Okay, so here's our picture. Now, first of all, the antiderivative, our area-giving function, is x cubed on 3. Increase the power by 1, divide by the new power. But the area is written like this, reflective of an infinite number of rectangles drawn from 0 to 1 under the curve x squared. We can't do that, but we know if we say that that is the antiderivative evaluated at 1 and then subtracted at 0, that was our definition of the area function, wasn't it? As long as we can find a function here whose derivative is that original function. We need the antiderivative. So we're going to stick this in here and put in 1 cubed over 3 minus 0 cubed over 3. It's a third square units. So we've got it all together in this notation. This is reflective of the infinite sum of rectangles between the x-axis going up to the curve. And this is the way we do it, by finding the antiderivative or the area given function, coming back and subbing those two values in. I'll do all these and then we'll come across and look at technology over on the right here. Let's do root x. There's the graph of root x from 1 to 9. Okay, that's x to the half. Increase the power by 1, divide by the new power. There we are. And if we wanted the area, we say it's the integral, the sum of an infinite number of rectangles from 1 to 9 under this function. How do we do it? We go to our area given function. That's the antiderivative, the function whose derivative is that. We're going to evaluate it at the upper end minus the lower end from our derivation above. So it's 2/3 by 27, just keeping in mind, if we put 9 in there, it'll come to 27. And if we put 1 in there, it'll come to 1. So it's 17 1/3 square units. And we've done it. So we have a theoretical statement. There's our theoretical statement. And we've now defined a function that will do that without approximating it, without trying to draw an infinite number of rectangles. Let's look at the Casio up here. How do you work this out on a calculator? Well, first of all, the first method up the top here is to put the function in graph mode. So here we are, we're graphing the function. Then what we do is go Shift F5 to G-solve and we get this picture. And if we hit the key there, F6, go to the next window, there it is. There's our sum of an infinite number of rectangles. So we hit that one, which is F3, and on pops arbitrarily an x value. So we put in 0 now, and it will come up, you want that to be the lower bound? Yes. And we execute that, and it asks for the upper bound. And we pop in 1, and we execute that, and it displays it and gives the area for a third square unit, 0.333. So do you like it? That's a way of doing it on the calculator. What about another way? This one's in just run mode. So go to run mode. Okay, here's the starting window. If down on the keyboard you hit options, that key, then up comes these possibilities. If you hit F4 for calculate, can you see there it is again, the integral? So choose F4 again and this symbol comes up. And all you have to do is enter the limits in there and the actual function in there. This is in run mode, and when you have entered those, you will get the same answer. So it's magic, isn't it? A lot of ways of handling this function. Okay, well let's have a look at some actual problems now. So I want you to try these. It's from Hayes and Harris. So draw a diagram and check your answers with technology. Remember, the area given function is equivalent to the antiderivative of the function whose graph you're drawing. Okay, that's very, very important that you use that. Okay, let's have a look here, the fundamental theorem of calculus. You can try and do these proofs. These are not in the course, but you can have a go at drawing the proofs and go back to your teacher. Just remember here, f is the antiderivative of f of x. It's treating f of x as a derivative and coming backwards. Okay, and further down here then, we've got some more, and check using technology. So have a go. This one's an interesting one. You could use technology because you can't actually integrate this at this stage, or you can calculate the area directly, because what's that? That's a semicircle. All right, and then down here, fundamental theorem of calculus, some interesting ones here as well. All right, so check those. You might like to go through that with your teachers. I'll show you the answers now and see what you think. Okay, so here are the answers to those problems. I hope you're getting excited here. It's getting a bit complicated going backwards from differential calculus to find that area function, but it's interesting to see the derivation, isn't it? And we're going to be doing a lot of applications with integral calculus. So I hope to catch you then. Cheers for now.